Hello everyone, welcome to my presentation entitled Placement-Aware 3D Net-to-Pad Assignment for Array-Style Hybrid Bonding 3D ICs. My name is Pruek Vanna-Iampikul from Burapha University. This work is a collaboration with my advisor, Professor Sang-Kyo Lim from Georgia Tech and Synopsys. Here is the outline of my talk. In today's chip industry, the 3D ICs have emerged as a competitive option for continuing performance improvement as the device scaling approach reaches its limits. And there are three types of the 3D integration. First, the TSV-based 3D ICs. In this approach, the dies are stacked on top of each other and connect vertically using the through silicon vias or the TSV and the micro bumps. However, this approach is limited by the large size of the TSV. They restrict the number of the 3D interconnection. Second approach is the hybrid bonding 3D ICs. The two fabricated dies are bonded face-to-face using the copper pads, while the TSV are still used to deliver the power through the multi-die stackings. And the third option is the monolithic 3D ICs. The dies are sequentially fabricated on top of each other and connected using the monolithic intertier via. This process requires the substrate thinning and is still under development. This work focuses on the hybrid bonding 3D ICs, a technology that has been commercialized in products such as Intel Foveros and the AMD 3D V-Cache. To implement the 3D ICs, there are two main approaches. First, the true 3D EDA tools. These commercial tools offer the 3D placement and routing capabilities. And second, the pseudo 3D flow. This approach leverages the commercial 2D EDA tools to build the 3D ICs. Since the true 3D EDA tools are not fully developed, many studies have proposed design methodology using the pseudo 3D flow. In the pseudo 3D flow, we can either design the die separately or integrate them later, or co-design and optimize multiple die together. Our focus is on the latter approach. Among the state-of-the-art 3D design flows, the 3D terminal assignment can be categorized into two groups based on when the 3D terminals are assigned. First, the assign first flow. The 3D terminals are fixed before performing the placement and routing or the PNR. And second, the assign last flow. The 3D terminals are assigned during the final routing stage by the routing engine. An example of the assign first flow is the Cascade 2D, as shown in the left, where the 2D dies are placed side by side, and terminals are fixed in the beginning using a bridge without the RC parasitics to connect them. In contrast, an example of the assign last flow is the Pin 3D, shown in the right, where the routing is performed at the final stage to determine the 3D terminal location. Based on the two types of the 3D terminal assignment, the assign first flow offers the scalability benefit for the multi-die integration, but suffer from the PPA power performance area issues due to the fixed 3D terminal locations. The assign last flow provides a better PPA, but face the design rule check or the DRC challenges, and may not be scalable since they require the 3D metal stack. To overcome these limitations, we propose the new approach that combines the advantages of both approaches. First, we enable the flexible 3D terminal placement within the assign first flow And second, enhancing the PPA, reducing the DRC violation, and to support the array-style hybrid bonding for multi-die integration. And next, we will explain the detail of our framework. Our framework extends Cascade 2D by enabling the 3D terminal movement through anchor cells and anchor constraints, while also supporting full array hybrid bonding for multi-die integration. The Cascade 2D flow consists of three main steps: partitioning, face-to-face planning, and 3D placement and routing. A comparison between our framework and Cascade 2D is shown in the right. In the first step, we model the 3D nets using anchor cells, building upon the concept introduced in the Cascade 2D, with additional settings to enable the 3D terminal movement. We classify the 3D net into two types: the movable 3D terminals modeled as the anchor cells, and the second fixed 3D terminal modeled as the path cells. The anchor cell is designed as a buffer, allowing the cell movement while maintaining the input and the output pin at the top. In contrast, the path cell is modeled as the cover cells, ensuring the fixed placement. In the second step, given the partitioning, we insert the feed-through nets to ensure that the external input and output are properly connected through either top or the bottom die. In this study, we route all the I/O connection through the bottom die. Once the feed-through net is inserted, we place the pairs of anchor cells to represent the 3D net. For example, in this case, the net connecting to the P1 to P3. A feed-through net is inserted to each die. Next, we ensure the correct alignment of anchor cells by introducing placement constraints. The first constraint allows the anchor cell to be placed within the memory region. In face-to-face 3D IC, 3D terminal can be flowed at the top. To enforce this constraint, we generate a special blockage that prevents standard cells from being placed in this region, while allowing the anchor cells. Additionally, we make the memory region transparent by dealing them as the cover cells, ensuring that they do not occupy silicon area while their pin remain unchanged. The second constraint ensures the correct alignment of the anchor cells pairs. In face-to-face die stacking, the top die is flipped downward to integrate with the bottom die. However, the distance between the anchor cells in different pairs varies, making it difficult to enforce placement constraints. To simplify the alignment process, we flip the top die vertically at its center point. As a result, the anchor cell distance becomes uniform, allowing us to constrain the top anchor cell to follow the top anchor cell. At this stage, the anchor cells are aligned, but the cells have not been legalized. To support the detailed placement, we can relax the anchor distance constraint by introducing the relative constraint using a move boundary. The anchors are allowed to move within the defined region, where the boundary size is determined by the stack of the 3D part. After the placement optimization step, we assign the anchor to grid location based on the user-specified face-to-face pitch. Since each 3D net contains two anchor cells, we select the driver cell as the 3D net location, and we remove any unused face-to-face grid location. Next, we will show the result of comparison of our work with state-of-the-art. We use the three commercial processors as the design benchmark with the different memory macro utilization to cover both logic on logic and memory on logic configuration. These three benchmarks are implemented using the advanced node technology at 5 nanometer and 7 nanometer PDK. The face-to-face pitch is selected based on the minimum pitch that can accommodate all the 3D net. First, we compare the impact of the terminal movement before and after placement optimization. The blue dot represents the face-to-face terminals. After the optimization, there are slight changes in both the number of the cells and face-to-face terminal location. Next, we evaluate the impact of 3D terminal movement on the PPA. Our results show that the design using our framework achieves better setup hold timing, shorter while length, and the lower PDP product to the design with the fixed 3D terminal. We perform the global placement using the different options and conduct the PNR in the cascade fashion to ensure the fair comparison. Our results show that our framework achieves better timing performance, particularly for the hold timing, and significantly reduce the DRC violation compared to the other approach. Lastly, we summarize our findings and key benefits of this work. Our framework enables the face-to-face terminal movement, which enhances the PPA while reducing the DRC violation compared to the state-of-the-art approach. Additionally, the framework supports array-style face-to-face placement, facilitating the multi-die integration. Please refer to our paper and live presentation for more detail. Thank you very much.